Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn about how engineers characterize the broadband frequency content of many sounds by reporting sound levels in terms of frequency bands.
So let's get started. We'll first overview human hearing sensitivity. Difference Lymans are what we refer to as the smallest perceptible differences in sound. For humans, the difference Lymans in terms of our ability to distinguish frequencies, the difference Lymans increase with the increase of frequency. What this means is that it is easier for us to distinguish between 100 and 150 hertz than for us to distinguish between 1000 and 1050 hertz. In other words, the 50 hertz change at low frequency is a larger relative change than at high frequency. This is an indicator that the difference Lymans in the frequency domain increase with increase in frequency. This is one reason that we often use logarithmic scaling, not only of amplitude, but also in the frequency domain, because this better matches human hearing sensitivity to frequency changes. To characterize these frequencies, we use bands, and specifically octave bands. One octave is a doubling of frequency, or a 1/2 of frequency. So we go from doubling or 1/2 of frequency. So 100 to 200 hertz. And octave bands help create logarithmically spaced frequency ranges. The octave bands that we use throughout acoustics have center frequencies. We denote these as F sub C, and they are computed as 1000 hertz times 2 to the power S. This is in hertz, where S is equal to the range of numbers, specifically integers, from -5, -4, 0, 1, ending at 3, and 4. We could also write this, for instance, as S is equal to -5 colon 4. If we work these out, we find that the octave band center frequencies are 31.25, which is often rounded to be 31, 62.5, which is often rounded to 63, 125, 250, 500, 1000, 2000, 4000, 8000, and 16,000 hertz. When the octave band center frequencies are plotted linearly as a function of a logarithmic scale, we see that the logarithmic spacings are constant, whereas the linear spacings are not. Yet this represents a more realistic characterization of human hearing sensitivities. In addition to octave band center frequencies, we define lower and upper frequencies around which the octave band center frequency is bounded. We use the lower and upper frequency limits to calculate sound pressure level in our reporting. The lower frequency limits for every octave band is given as F sub L for the ith band is the center frequency for the ith center frequency times 2 to the power minus 1/2. That is in hertz. In addition, we have our upper frequency limits. Upper frequency limit. These are expressed as f sub u to the index I for the ith center frequency. It is equal to the ith center frequency, f sub c superscript parentheses I, times 2 to the positive 1/2 power. That is in hertz. So when we sum for the 1 kilohertz octave band, we sum pressures from 707 hertz to 1,414 hertz. We could compute the lower and upper frequency limits with ease by using these formulas. They're shown here on this plot. We also see that the lower frequency limit for one band is the upper frequency limit for the octave band below it, and so on and so forth. The lower is equal to the upper of the adjacent band. Once we have our lower and upper frequency limits for the ith octave band, we can find our overall squared RMS acoustic pressure, which is simply a sum of the RMS square pressures. We can then sum over a given frequency range, such as what we might have for the 1 kilohertz octave band, from about 707 hertz to 1414 hertz, to find our overall sound pressure level for that specific octave band. We see in this example that to find the P squared RMS for 1 kilohertz, we must sum from the frequencies 707 hertz in our narrow band plot of red data up to the upper limit of 1,414 hertz of the P RMS squared pressure for each frequency increment in between the lower and upper frequencies. It is important to recognize a few requirements for these calculations. Firstly, this is a sum. It is not an average of squared RMS pressures. It is a sum. It is also a sum from the lower to upper and frequency limits, without exception. In other words, if not all of the frequencies are available in the data from a lower to upper limit, we cannot compute the octave band result. It doesn't mean all integer frequencies must be available in the data, but we simply cannot cut short on the lower side or higher side of the frequency band. Let's use an example to understand. Let's say at the workplace, a colleague provides us frequency data of some acoustic recording that has been converted by an FFT to the frequency domain, and the frequencies provided go from 100 hertz to 5,000 hertz. What octave bands can we report? If we look at this table here, we see the lower and upper frequency limits for all of the bands. Let's consider the lower limit of the frequency data our colleague provided. It is at 100 hertz. For the 125 hertz octave center frequency, we find that the lower limit is 88 Hertz. This means that we are unable to go all the way down to 88 Hertz given the frequency data we've been provided. So the lowest of the octave bands that we can report is 250, since 176 and 353 would both be included in the available data. Likewise, at the high end, at 5000 Hertz. If we look at the 4000 Hertz center frequency, we must have data up to 5656 Hertz, but we do not. So the highest center frequency we can report is 2000 Hertz, since both 1414 and 2828 Hertz are available in the data. This is an example that shows we must have the full range of lower and upper frequency limits available in the data in order to compute a given octave band center frequency sum. For greater frequency resolution, sometimes we'll find 1/3 octave bands reported. The levels are computed in a similar way as with octave bands, but the center and limit frequencies are different. The center frequencies we'll report or write as f sub c 3 are equal to 1000 times 2 to the s hertz, where s is equal to the range of -15 to +12 divided by 3. The lower limit, f sub L3 to the ith for the ith 1/3 octave band center frequency, is f sub C3 to the ith center band times 2 to the -1/6 Hertz. The upper frequency limit, f sub U3 to the power I, is equal to f sub C3 to the power I times 2 to the 1/6 Hertz. When we perform this routine, what we find are that the 1/3 octave band levels shown here in the magenta triangles are less than the octave band levels. This makes sense. The octave band computation adds up the overall acoustic pressure. This means that octave band levels will always be greater than the narrow band or the distinct per frequency data recordings. This also means that 1/3 octave band level results will always be less than octave band levels, but they will be greater than the narrow band result. So anticipate this type of trend when computing your own 1/3 octave band and octave band sound levels. The overall sound pressure level, sometimes written as OASPL, is a very common way of reporting the overall sound from 20 Hz to 20 kHz. In other words, over the range of human hearing. The way to calculate OASPL is similar to what we've seen with the octave bands, but now we simply sum over the entire frequency range. But we don't need to limit ourselves to calculate the sum from 20 Hz to 20 kHz. Very often, we'll compute OASPL so long as all of the sound levels are concentrated in the frequency range that we're actually measuring. For instance, we might be in an environment where the sound levels truly only contribute from about 100 Hz to 4,000 or 8,000 Hz, in which case we can neglect frequencies below 100 Hz, we can neglect frequencies above 8,000 Hz, and only take our OASPL evaluation from 100 to 8,000. If we run an OASPL computation for the plot that we've been seeing here, and is now again shown on the bottom right, our OASPL is 79 decibels. What's important when we view it in terms of the octave band values and 1/3 octave band values, and finally the narrow band values, the OASPL is larger than all of the other dB values reported. Again, this makes sense. It is not an average, it is a sum, so it collects all of the sound energy into one value. Interestingly, the highest of the octave band values are almost the same as the OASPL. It is important to recognize that the sound quantities we're dealing with are logarithmically presented in the decibel scale. So that means the values that are highest many times greater than the ones that are lowest. So for instance, the values around 40 decibels are 2 orders of magnitude less than the highest values presented here in terms of acoustic pressure amplitude. So very often we anticipate that the OASPL value will be dominated by the highest of the octave band values. Let's summarize what we've learned. For broadband frequency sound, humans have a difficult time distinguishing the frequencies of sound, so we often report sound pressure level in octave bands or 1/3 octave bands. These sum the RMS squared pressures over a frequency window, after which we compute the sound pressure level in decibels. OASPL is similar in calculation, but it is performed over the whole audible or meaningful frequency range, and OASPL is the common way of reporting sound in noise control practice and regulations.
That's it for this video. In the next video, we'll learn how sound levels are weighted to account for human hearing sensitivity.